Our new topic is when we're going to begin our look into calculus. When at the end of the day, the course that you've chosen to do here is what is called a calculus-based course. So now that we've spent a whole heap of time looking at algebra and how to manipulate that and how to find things on the number plane, and we've looked at a couple of different types of functions and a fair bit of trig as well. We can now start and get into this idea of calculus itself. Calculus really didn't come around until they solved this idea of what a limit is. So let's just talk about this for a bit. All a limit does is it describes how a function, or if you like, the picture on the number plane, how it behaves, what it does. What value does it approach as you move, and things like that. So some notations. This is the standard way of writing it. We write limit, or LIM for limits. Then underneath it we say, well, as the x value, so x, approaches, we draw an arrow, and then a particular value. So as the x value is getting closer and closer and closer, we want to know what the function is doing. So if I'm talking about a picture, I'm saying, well, as I get closer to this x value, what y value is the graph getting close to? That's basically what it's saying. Okay, so as the x value approaches a, what's the function doing? Sometimes you can investigate it from either direction, because sometimes it's not the same. Classic example, I guess, is the hyperbola over there. If I was to investigate what happens as x approaches 0, if I was to approach it from the negative side, and that's what this notation means, approach a from the negative side, well, then the y value on the hyperbola would be approaching negative infinity. It's right down the bottom. Here's an absolute value graph. If I approach it 1 from the negative side, well, then the y value is approaching 0. Then I've got one of those classic sort of step graphs where there's a break. If I approach 0 from the negative side, that one's approaching 4. So with our hyperbola over there, I'd go to positive infinity rather than negative infinity. So when you have a discontinuity or an asymptote, you can approach different values. If the curve's continuous, they would approach the same value. And that actually is our definition of continuity, which we'll see in a second. So with these two graphs, the absolute value graph, yep, it's the same. Approach from the positive side, I'll get 0. Whereas my step graph there, approach from the positive side, and I would get 6. Okay. And so that basically is our definition of whether a curve is continuous or not. So if those limits are the same, then a curve would be continuous. Now, we don't really have to worry too much about that in this course, about from the positive side and the negative side. We usually just look at a limit as such. So how do we find limits? Direct substitution is the easiest way. I mean, if you've got the equation of a function, substitute the number in, and you're going to see what y value it goes to if it is defined at that point. So if I just simply was looking at this line, x plus 7, there's the graph, and I want to know what's happening as x approaches 5. Well, I'd just substitute in 12. The y value must be approaching 12. And that's fine, so long as you've got a nice continuous graph. That will work. The next idea is to factorise and cancel. If I was to substitute this one, x squared minus 9 on x minus 3, that's one of those graphs that will end up having a point discontinuity at 3. So it doesn't actually exist at 3, because if you put it in the bottom of the fraction, we get 0. So I can't just directly substitute into that, because I get that classic problem in maths of 0 on 0. What is that? Is it 1? Is it 0? Is it infinity? I mean, who knows? Correct answer to that is nobody, actually. But anyway. But in this case, we can factorise it and then cancel the x minus 3s and then do a direct substitution. And that would tell us, well, okay, it doesn't actually equal 6. So what we know is with this graph is that, okay, if I were to look at the picture, it would be getting closer and closer to 6, but it wouldn't actually exist at that point. That would be, in this case, a point discontinuity at the point 3, 6. we have a special limit which allows us to investigate something more interesting. Because one of the really important things we think of with graphs is where do they start, where do they finish? In other words, what happens out at infinity and minus infinity? I mean, how do you substitute infinity into something? Which you can't, but we sort of can. What? Because we know the picture of the hyperbola. We know what that looks like. So I actually know that limit. As x approaches infinity of my hyperbola 1 on x, I know it's getting closer and closer to 0. So if it was possible to reach infinity, then it would be equal to 0. Using that limit, I can find all sorts of other limits. Say I had this particular graph to draw, x cubed plus 3x squared plus 2x minus 1 on 4x cubed minus 1. And I wanted to find what it was approaching. Basically what I'm looking for here is what would the horizontal asymptote would be. So yes, a polynomial division would achieve the same thing. I could do that, and so my answer will end up being, if I did a polynomial division on this, a quarter, I think I get. But if I use this idea, if I substitute infinity into this, okay, infinity is really big. Okay, I substitute it into x cubed, so that's infinity cubed. That's really, really, really big. So I'll get infinity cubed, and I'm going to add 3 lots of infinity squared. So now it's like really, really big. And then I'm going to add another 2 lots of infinity, massive, like huge, and I'm going to subtract 1. So what? Yeah, I mean, huge, absolutely huge. And then I'm going to divide it by something which is also really huge, 4 times infinity cubed minus 1. So I've got this really huge number, and I'm dividing it by this other really huge number. What's the answer? Well, who knows? I do. I don't substitute into that. I'll substitute into this instead. As long as I do the same to the top and the bottom of the fraction, I'm okay. I'm going to divide by x cubed. Now, the reason I chose x cubed, that's the highest power that's there. Because then every one of those individual fractions will cancel to leave x now in the bottom of the fraction. But my special limit says whenever I substitute infinity into the bottom of the fraction, the answer will be 0. As long as I've got a constant on top. Well, have a look at what we've created. All of these are fractions where there's a constant on the top, x on the bottom. So I know every one of those fractions will approach 0, leaving me with 1 on 4, a quarter. There's the answer. The reality, of course, then is I don't actually need to divide everything by x cubed, because the key is the highest power. So when I look at my original one, all I really need to do is ignore everything except for the highest power. So if I do that, I've got x cubed on 4x cubed. Oh, that cancels, a quarter. So if I have 4x minus x squared on x cubed plus 1, I'm going to ignore everything except the highest power. And so I end up with 0 on x cubed, which would be 0. 0 is on the top of the fraction. It would end up being 0. 0 on 1, because the coefficient of x cubed is 1. 0. If I put it into this one, x to the power of 7 plus x to the power of 6 plus x squared over 3x to the 7 minus x minus, let's pick a really big number, 974, which actually in the scheme of things is not that really big, because we're talking about infinity. 974 is actually very small compared to infinity. But ignore everything except the highest power. Highest power there is x to the power of 7. So I've got a third. That one will go to a third. What about this one? X cubed plus 2 on x squared minus 1. Ignore everything except the highest power, or the coefficients. I'm going to end up with 1 on 0. Well, it's back to that idea like the hyperbola. Well, 1 on infinity was 0. So we think of 1 on 0 like infinity. Infinity is another one of those strange numbers, but if it's undefined like that, division by 0, we tend to think, oh, well, it's obviously going to be very, very big. It's going towards infinity. So if I now get a question like this, find the horizontal asymptote, I can now use limits. Polynomial division will still work. I mean, you could do it that way. But now I could do it via limits. I don't actually have to do the division. If I did have a look at this, remember, all I'm looking for is the highest power. What's the highest power on the top? Yeah, if I was to expand that whole thing out, I'd get x squared. What's the highest power on the bottom? So overall, I'm just looking at x squared on x squared, which is, there's my answer. Right? So I could expand it out if you don't believe me. Look, they really are x squared, top and bottom. And we're just looking at that. So, oh, well, 1 on 1. Yes, it's 1. So I can save a little bit of time if you use limits rather than a polynomial division. But remember, the only time you're going to get a horizontal asymptote is when that limit exists. If I had one where it came out to be infinity, that's one where I'm going to have one of those oblique asymptotes. And so if you did a polynomial division, you'd probably end up with x or x plus 2, and so x plus 2 would be the asymptote. So you'd still have to do that type of one with a polynomial division. But so long as the power on the, get this the right way around, so long as the power on the bottom, yes, power on the bottom is the biggest one, then you're right, limits will work to find a horizontal asymptote. There it is, y equals 1. All right, 7i. So before we start calculus proper, we'll just look at this idea of limits, because what we look at tomorrow does depend on knowing what a limit is. Right.